This energy example, this one comes from 2009 AP Physics C Mechanics. So it tells us there's a 3 kilogram object moving along the x-axis in a region where the potential energy as a function of x is given by 4x squared. The potential energy is measured in joules, x is in meters, and we're told here as the object passes this position of negative 0.5 meters, the velocity is 2, and all forces acting on the object are conservative. So what that tells us there is that our total energy quantity will not change. And A says calculate the total mechanical energy of the object. So for A, we know that there's going to be potential energy and there's going to be kinetic energy. What we're going to use is we're going to use this negative 0.5 meters for the potential energy, and we're going to use the 2 meters per second for the kinetic energy. So the potential energy is 4.0 times negative 0.50 squared plus 1/2 times 3 times 2 squared. The reason being is a reminder, kinetic energy is a 1/2 mv squared. There's your m, there's your v. So we got a calculator time to solve this one out. I will do 4 times 0.5 squared plus 1/2 times 3 times 2 squared, and I get 7 joules. So 7.0 joules, that's A. B says calculate the x-coordinate of any points at which the object has 0 kinetic energy. So again, our energy comes in the form of potential and kinetic, and we were just told set that kinetic to 0. And in part A, we just solved that the total energy is 7 joules. So 4.0 x squared equals 7. So x squared will be 7 over 4, which is 1.75. And then we take the square root of that, and we get x would be plus or minus 1.32 meters. So far, so good. We will move on to question C. It says calculate the magnitude of the momentum of the object at 0.6 meters. So energy and momentum oftentimes blend together in AP Physics C for mechanics. So it's basically impossible for me to find a question that's pure energy or pure mechanics. For C, we are given the position of 0.60 meters. So that's going to tell us our potential energy. Potential energy is 4x squared. So that'll be 4 times 0.60 squared. Our potential energy at this point is 1.44 joules. So potential plus kinetic has to equal 7 joules. So 1.44 plus our kinetic equals 7 joules. What I know is my kinetic energy, 7 minus 1.44, is 5.56. So I have 5.56 joules of kinetic energy. Why do I care if I'm looking for momentum? Because the kinetic energy is going to tell me what the velocity is. So 1/2 mv squared. And once I know that velocity, then I can go ahead and say the momentum is mv and solve for the momentum. The mass is given as 3. And I will solve the velocity of this object, 5.56 divided by 1/2 divided by 3. Take that quantity, put it under square root, 1.93 meters per second. 1.93 meters per second. So our final step then, I'm running out of room, but hey, we'll make it. P equals mv. The momentum will be 3 times 1.93. So 3 times 1.93 gives me 5.79 Newton seconds. Ooh, that was not a good 5. 5.79 Newton seconds. Box it and declare victory. Moving on to part D, calculate the magnitude of the acceleration. So the word acceleration makes me think forces, F equals ma. in order to get the force, I'm going to need to take the derivative of the potential energy. To remind you, if you integrate force with respect to displacement, you would get potential energy. So if I take the derivative of the potential energy, I would be left with the force. Well, what is the derivative of the potential energy with respect to x? That's going to be 8.0x, and that's my force based on the displacement. We are talking about the position of 0.6. So 8.0 times 0.60 is the force present. 8 times 0.6. The force is 4.8 newtons. And F equals ma. So F equals ma. 4.8 equals 3a. The acceleration, 4.8 divided by 3, is 1.60 meters per second squared. The last part of this is part E. Whoops. So let's go into here for part E. And we'll put this into the paint doc. No, why not just do it over here? Okay, so E says on the axis below, sketch the graphs of the object's position versus time and kinetic energy versus time. And we are told that at time of 0, the initial position is 0. The two graphs need to cover the same time interval. So that means our t-values have to line up together. Now this thing oscillates back and forth. So we are going to see something kind of sinusoidal for the position. Now this is where it gets very tricky because the kinetic energy is maximized at any time the potential is minimized. And the potential is minimized at any of these positions in which the position is 0. To remind you, the position determines the potential energy. So if x is 0, the potential energy is 0, and that would result in us having a maximum kinetic energy at all of these positions. The other thing that's worth noting is when this changes direction, which is here, here, and here, we have gone ahead and maximized the potential energy, and therefore we would expect the kinetic energy to be 0. So that kind of helps shape this graph. It is going to be sinusoidal in nature. Comes down, comes up, comes down, comes back up, comes down, comes back up. It's also always greater than or equal to 0 because it's kinetic energy.